home. All right, so it's a great pleasure to have with us today Nick Stone from the Hebrew University in Jerusalem. I personally happen to know Nick for something like 10 years, right? Yeah,
something in that ballpark.
Since he was a graduate student at Harvard at the CFA Center for Astrophysics with Avi Leib. He then moved on to Columbia University as to go to the prestigious Einstein Fellowship. And he was there for 5 years. And then he got it since 2018, 19. Echo, which I don't know how to handle. I will.
You mentioned earlier in the interview.
Handling it?
Looking home and
right. So after that, Nick spent.
Mute that one.
Did it. Your mic is on?
Over here.
My microphone, I thought I turned it off. It's off.
Oh, there's
Es el volume se la
The speaker.
Oh, that could be it.
That's a feedback.
Okay, now it's off.
Now it's off.
Sorry for that.
Okay, so yeah, so after right after graduating, Nick spent 5 years in Columbia as an Einstein fellow, and then he moved to Hebrew University, right? So
Asaf, thank you very much for the invitation. I guess the reverberation is not that great. Can you turn off those speakers?
Yeah, this is what I tried to do.
Then we cannot.
I guess we could turn that on at the end for a Q&A.
You should have come here.
Right now.
Why not mute the...
No.
No. Is the feedback? Yeah.
Okay.
We can't hear anything.
Hello?
Okay.
יכול להיות שזה המיקרופון בעמדה שתופס משהו כזה.
All right, so hopefully they can hear me through my microphone. All right.
Okay. Sorry about that.
Do the people at home hear you?
Yeah, they should be able to hear you now.
Okay, coming back to the physics. The three-body problem is arguably the oldest open problem in mathematical physics. It dates back to Isaac Newton's Principia Mathematica. After Newton solved the gravitational two-body problem using the conic sections we all learn about in our first year of physics, he quickly realized that it would be interesting to consider what the motion of three Newtonian point particles looks like, all interacting via their mutual gravitational fields. I've copied and pasted the relevant section of the Principia, but to make a long story short, Newton didn't get very far. Of course, in the centuries after Newton, many astrophysicists, physicists, mathematicians spent a great deal of time studying and gaining insights into the nature of three-body dynamics in Newtonian gravity. But the problem is that in order to make analytic progress, traditionally, we've needed to invoke some sort of hierarchy. This can be a hierarchy in mass. Maybe one object is much smaller or much bigger than the other two objects, but it can also be a hierarchy in separation, as long as it's a durable hierarchy in separation. What I mean by this is if one of the three objects, and let's say they're all of comparable mass, is always very far away from the other two objects, then the system decouples into two weakly interacting two-body problems. However, of course, sometimes in nature, we get a non-hierarchical three-body problem where three objects of comparable mass don't have this kind of durable hierarchy and separation. When this happens, we'd still like to know what the time evolution of this system is, what the final outcome is. And these questions in the late 19th century led the King of Sweden, Oscar II, to offer a substantial cash prize for anyone who could write down some sort of closed form solution for the non-hierarchical three-body problem. The search for these solutions came to an end when the prize was awarded to Poincaré, essentially for demonstrating that no closed form solutions exist. Poincaré showed that the non-hierarchical three-body problem is, in modern language, a prototypical example of a chaotic dynamical system. And it's the fundamentally chaotic nature of the non-hierarchical three-body problem that makes the analytical techniques used in the past, essentially various forms of perturbation theory, break down. That's because in dynamics, saying that a system is chaotic isn't just a colloquial statement. It means that the system exhibits exponential sensitivity to tiny perturbations in initial conditions. And so the normal tools of perturbation theory are not very useful for deriving deterministic solutions to such problems. So in the absence of real closed form analytic solutions, most of what we know about non-hierarchical triples comes from decades of numerical experiments. Beginning in the 1960s, people have just used modern computers to brute force integrate the equations of motion, as you saw in my title slide and as you can see here. What these many numerical scattering experiments have shown is that non-hierarchical triple systems are at best metastable. They can exist in a bound state for some period of time, but except for initial conditions of measure zero, the long-term outcome is always disintegration. The non-hierarchical triple breaks up, usually into two bound stars that leave as a binary, and one escaping single star that leaves as a singleton. one other thing that comes out of studying these numerical simulations, let me go back, is that the evolution of the triple is what is sometimes called intermittent chaos. So you have brief periods of time, which in modern language are called scrambles, when all three objects are in roughly the same volume. But then you have longer periods of time like this one, where the system has decoupled into two weakly interacting two-body problems, but that decoupling comes to an end when the tertiary comes back to its pericenter and interacts with the binary. So the periods of intense chaotic evolution, the scrambles, we'll come back to these later, but one heuristic way to define them is as periods of time where no pairwise binaries exist. So the entire system has negative total energy, but in a pairwise way, no two objects are bound to each other. Okay, so that's a single numerical scattering experiment. But with modern computers, we can of course do better than that. And what's shown here is a surface of section representing the outcomes of roughly 1 million numerical scattering experiments. So here, the initial conditions for the experiments are shown on the X and Y axes. The initial phase of the target binary is on the X axis, and the relative inclination between the target binary and the impactor, which has an impact parameter of 0 here, is shown on the Y axis. The color coding represents the lifetime of the metastable triples that are created. Black is very short, you don't actually create a metastable triple, and yellow is very long. It's a long-lived system which lasts for many dynamical times. What we can see is that this is the kind of surface of section that may be familiar to you if you've studied chaotic dynamics in the past, in that we have islands of regularity floating on top of a chaotic sea. What do I mean by that? You have these large coherent patches, the black ones, where the outcome is essentially deterministic and quasi-regular. The reason for that in these large black patches is that the impactor comes in and just flies right through or kicks out one of the initial binary components, and one of those gets ejected promptly. So there's no opportunity for one of these scrambles with a long duration of chaotic evolution to actually set in. We can zoom in on a smaller part of phase space, and what we see is a self-similar fractal structure. Individual bands of relatively short duration correspond to systems where the ejection happens not on the first close encounter, but instead on the second. So a metastable triple forms, but the second time a star comes back, so the first time you have a scramble, the system promptly disintegrates. That's the meaning of the thickest band. The next thickest band would be one that lasts for 2 scrambles, 3 scrambles, and so on. And if you zoom in, you'll see this fractal structure wherever you go in phase space, as long as it's not in one of the large islands of regularity. Okay, was there a question back there? Oh, all right.
How do you know that it really disintegrates at the finite time?
Well, you can look at the total energy of the system after one of these ejections. So when you still have a metastable triple, the 3 stars are bound to each other, but the final terminal escape means that one of the stars has been kicked out with positive orbital energy, so it's never coming back. It's essentially an energy criterion that allows you to determine when the disintegration has truly happened. Okay, so you can learn lots of interesting things by looking at the outcomes of these numerical scattering experiments, especially in a statistical way. Since we started a little late, I'm going to gloss over the details here, but you can come back later if you're interested. I do want to speak a little bit about the astrophysical motivations for studying this. So these kind of non-hierarchical triples show up all the time in astrophysics. Multiple star systems during their formation often pass through a phase of chaotic non-hierarchical evolution. Exoplanets can go through similar processes. Even triples of galaxies and galaxy clusters can participate in qualitatively similar dynamics. But in contemporary astrophysics, I think the most exciting motivation for studying these systems is to learn about the origins of gravitational wave signals in the universe. Right now, there's a very interesting question in relativistic astrophysics, which we don't know the answer to. The LIGO and Virgo experiments are seeing tens of gravitational wave signals a year, mostly from binary black holes merging, but where are these binary black holes coming from? Astrophysically, this is a surprisingly difficult question to answer because isolated binary evolution has a hard time doing it. So one popular theory explaining where most of the rate is coming from is through iterated binary single scatterings in dense star clusters, such as the centers of galaxies or clusters that exist elsewhere in galaxies, where the typical binary star system or binary black hole system can be expected to have dozens of strong binary single scatterings that produce metastable triples over the age of the universe. What's shown on the right here is sort of the stylized output of a very detailed Monte Carlo dynamic simulation of what life looks like in one of these dense clusters. And you can see the sequence of dozens of multi-body interactions, binary-binary scatterings, binary-binary exchanges, binary single exchanges, binary single scatterings. These are the most important ones that follow a binary black hole system from the birth of two isolated black holes all the way down to the final merger of a very tight binary due to gravitational wave emission. There are other applications for this also. We can talk about this at the end if people are interested, but this is in many ways the motivation that spurred me to think more about this old problem in physics. It is an old problem in physics. You can find many standard references on the three-body problem, both in the hierarchical and non-hierarchical limits. This textbook by Maury Valtonen and Hannu Karttunen is, in my opinion, the best of these references out there. If you're more interested in getting alternative perspectives, the Chinese science fiction community has its own well-known work on this subject. Okay, so that's all I have to say by way of introduction. Are there any questions right now before I go into my own work? Asaf?
Is any three-body unstable?
Not any system. So you can show that as long as there's a large enough hierarchy in either mass or in separation, there are systems which are indefinitely stable. Proving this mathematically is difficult. This is the origin of this question is the origin of KAM theory, Kolmogorov-Arnold-Moser theory for thinking about nearly integrable systems and their long-term stability. But you can show that as long as the hierarchy is strong enough, there are systems which are stable in the long-term sense. A good question. Another?
Is this stability fine-tuned for a single point, or is there a region of stability?
It's not fine-tuned. As long as you have a big enough hierarchy, there are non-measure zero sets of initial conditions, which are long-term stable. Also a good question. Another?
What is the probability that a three-body system will remain infinitely stable?
That's a tough question to answer because it depends on the initial conditions you're talking about. When you say probability, that implies you have some distribution of initial conditions. For some distributions, you have many stable triples. For other distributions, you have many unstable ones. Okay, I think that question, although I couldn't give a very satisfying answer, is actually a very good segue into my own work, because what my collaborators and I realized a few years ago is that even though the chaotic nature of non-hierarchical triples frustrates deterministic pen and paper solutions and is really the key reason why perturbation theory doesn't work, this strongly chaotic aspect of the three-body problem can actually turn into a tool if you're willing to give up on determinism and settle for a statistical solution, which in many applications is just as valuable. The basic idea here is that chaotic dynamical systems are often ergodic. Now, here I'm talking about ergodicity in the thermodynamic sense. There are a couple of different ways to define this, but for a practical perspective, what this really means is that the dynamical system is forgetful. It forgets all of its initial conditions if it's allowed to evolve far enough in time, except for conserved integrals of motion. Other initial conditions are basically nuisance parameters for a strongly chaotic dynamical system, which will be forgotten. Here, the integrals of motion which are conserved are really just the total energy E naught of the triple and the total angular momentum L naught of the triple. So in principle, as long as we know these two things, we should be able to compute a statistical solution that instead of mapping one set of initial conditions to one final outcome, maps a distribution of initial conditions to a distribution of outcomes. And when I'm speaking about outcomes, I'm talking about the properties of the final state after the triple is disintegrated. So for example, what is the probability that you have a circular binary left over as opposed to one with an eccentricity of 0.7? What's the probability that the escaping single star goes that way instead of that way? These are the kinds of continuous outcome variables that, in principle, we should be able to figure out as long as this is a sufficiently chaotic system, one which is thermodynamically ergodic. The way to do this is to, the way that we've come up to do this is to compute the very high dimensional phase volume of the system at the moment of disintegration. So let's talk about this equation. I don't have too many equations in this presentation. This is the only one we're going to really dwell on. The three-body problem is in three-dimensional space an 18-dimensional problem. We have three classical Newtonian point particles, each has 6 phase space coordinates. By switching to relative coordinates, or equivalently a center of mass coordinate system, we reduce the dimensionality to 12. This comes basically from conservation of linear momentum. These 12 dimensions are what's shown in the integral here. So dr and dp are the relative position and relative momentum of the two stars in the surviving binary, the position and momentum relative to each other, whereas rs and ps are the position and momentum of the escaping single star relative to the binary center of mass. So we have some sort of 12-dimensional space in which the outcome variables we care about live. We can compute the total phase volume that's occupied by a hypothetical ensemble of many different metastable triples with arbitrary initial conditions, but the same integrals of motion by doing this integral. However, fundamentally, the outcome space is living on an 8-dimensional hypersurface in this 12-dimensional space. The reason being that we need to conserve one scalar integral of motion, E naught, and one vector integral of motion, L naught. So what these Dirac delta functions do is they say that after the system breaks up, you have a surviving binary with some energy EB and angular momentum LB, and you have an escaping single star with an energy ES and angular momentum LS. And we need to make sure that these add up to the integrals of motion, which were conserved through the chaotic dynamical phase that preceded the disintegration of the system. Now, we have a question in the back.
Yeah, so why is the integral in the final state not the initial state?
Good question, because fundamentally what we're interested in are the outcome variables associated with the final state. So what we're doing, I was going to get to this in a second, but your question is a very good opportunity for me to clarify this. What we're doing is we're assuming that non-hierarchical triples evolve ergodically, meaning that if we prepare a hypothetical ensemble of many different non-hierarchical triples with the same mass triplets and the same integrals of motion, but otherwise arbitrary initial conditions, we can evolve them forward in time and stop each system at the moment it disintegrates. And the probability of finding one system in a little cell of this 8-dimensional hypersurface is essentially uniform. We have an equal probability per unit, per differential phase volume of finding a system in any one of these differential phase volume cells. That's the fundamental motivation by this. Does this make the...
So the volume at the end is the beginning of the same.
It is, but it's the volume at the end that we care about, since theoretically we know the initial conditions. And in physics, I mean, the initial conditions are something that's given to you. You want to know the final outcome. Good question. Asaf?
Is there any possibility that all three objects will disintegrate, or there's always one binary, not one single?
Yeah, that's an excellent question. It depends on this total energy E naught. If E naught is negative, it's energetically forbidden for 3 single stars to escape. But if E naught is positive, that becomes a possible outcome. Usually, for the kinds of binary single scatterings in dense star clusters that might be making LIGO's gravitational wave sources, E naught is always negative, and it's not close. So we've focused on that part of the problem. But in principle, you could do a variant of this approach for the situation where there's a different decay channel into 3 single stars. Good question. Okay, so essentially what we're doing is computing a microcanonical ensemble. We're saying that we have some known phase volume that this hypothetical ensemble of non-hierarchical triples lives in. And if we care about the distribution of its properties at some moment in time, say in the far future, we can just evaluate the volume of this microcanonical ensemble in the phase space that we care about. I should note that this idea was not originally proposed by us. It goes back to J.J. Monahan, who's better known as a numericist. He proposed it in the 70s, but the difficulty of doing this integral in closed form, as well as some conceptual confusions, prevented him from succeeding. And the idea was sort of forgotten for a long time. Now, what are these conceptual difficulties? One problem is that this isn't exactly the microcanonical ensemble that you learn about in equilibrium statistical mechanics. So normally with a microcanonical ensemble, you're thinking about a many-body problem where you have some number of particles n that are all interacting with each other and n is much greater than 1. Here, we're thinking about an imaginary microcanonical ensemble of many different few-body problems. Mathematically, it's the same, but physically, it's different. This is a little closer to the Hauser-Feshbach theory of statistical decay rates for radioactive isotopes. The second conceptual problem, and the bigger one, is that the existence of this ensemble is not obvious from first principles. What do I mean by that? Well, what I mean is that gravity is a long-range force. So things like entropy for multi-body gravitational systems are not extensive variables. The long-range nature of gravity means that on a hypersurface of fixed energy, the phase volume and entropy accessible to a system is actually infinite. Now, what saves us here and what makes this a mathematically well-defined approach, what keeps the phase volume sigma from blowing up to infinity, is the fact that there is a well-defined moment of disintegration for all of these systems. There's a point in time when they break up, and that prevents the phase volume from going to infinity as time goes to infinity. But this was a big source of confusion in the past. Now, just to put all of our cards on the table, I want to list the key assumptions that go into this procedure. There are three main ones. The first is that there is a well-defined moment of disintegration. So there's a point in time where the triple breaks up, and we're approximating it as instantaneous. This turns out to be a pretty good assumption if you compare it to detailed integrations of the equations of motion. The second assumption is that we're talking about Newtonian point particles. Again, this is a good approximation for many astrophysical problems. For others, where short-range forces matter, like general relativistic corrections to gravity, maybe it becomes less so. But for most astrophysical problems we care about, even including gravitational wave binary formation, this is a surprisingly good approximation. The third approximation is the biggest one, which has to do with the limits of integration. So we need to say, in defining the moment of disintegration, we need to have something concrete to put into the limits of integration. What we say is that the moment of disintegration happens, one, so following up on the question earlier, when the total energy of the tertiary star has become positive, and two, at a moment in time when the pericenter, Q sub s, of the tertiary star, the one escaping, is still within some sort of strong interaction radius, which we call R. It's a dimensionless fudge factor alpha times the time average size of the surviving binary. Now, this is the one part of our statistical formalism which is a little less than ideal. We're introducing a free parameter. It's a little bit of a fudge factor. Fortunately, we find out later on that our final results, the distributions of outcomes we predict, are not actually that sensitive to this free parameter, but it is a weakness that we've kept in mind throughout this. Okay, so without getting into the gory details, we found a pair of canonical transformations that make it possible to do this integral in closed form, something that wasn't appreciated in the past. What we find is that the distribution of outcomes is fundamentally trivariate. What do I mean by this? I told you earlier that the outcomes live on this 8-dimensional hypersurface. But if you switch to the right action angle coordinate system, you find that 5 dimensions on that surface are boring angular variables that are uniformly and isotropically distributed. So on that high dimensional phase space for outcomes, 5 of the dimensions are not very interesting. They're just uniformly distributed angles. 3 of the dimensions are interesting. And this is basically what the probability distribution of outcomes looks like. So after integrating over the 5 boring angle variables, we're left with a triple integral. The integrand of this integral is our probability distribution. This is the probability of finding individual, of finding a disintegrating 3-body system in a little cell of phase space where EB is the energy of the final binary, LB is the angular momentum of the final binary, and CB is the orientation of the final binary. So it's the cosine of the binary's orbital plane with respect to the reference direction supplied by the total angular momentum of the problem. So EB is energy, LB angular momentum, CB is cosine orientation. These are the three non-trivial variables that define the distribution, the statistical distribution of outcomes for the non-hierarchical three-body problem. And the beautiful thing is that you can write down this distribution in closed form. It's just the integrand right here. Realistically, there's a little more. This is the full distribution. It's not quite as pretty, but the formula on the previous page captures the important parts at leading order. Okay, so we came up with this closed form distribution. It looks very nice. It will be fun to apply this to astrophysical problems. But as I admitted to you, we made some assumptions along the way. And of course, we want to test how well this closed form solution corresponds to reality. The way we did this test was by running large ensembles of numerical scattering experiments, akin to the things I showed you at the beginning of this presentation. So specifically, all right, so in order to make this comparison as rigorous as possible, we want to separate out our numerical scattering experiments into two categories. Specifically, what we want to do is separate the islands of regularity I told you about initially to the chaotic sea. These islands of regularity where you don't even form a metastable triple. So a single star comes in, it hits a binary, it flies through, or it kicks out one of the binary components. These things don't go through any chaotic evolution, so we don't expect them to actually be well described by our ergodic formalism. On the other hand, if the system lasts long enough to undergo one scramble, which as a reminder is this brief period of strongly chaotic evolution where no pairwise binaries exist, then we expect the ergodic hypothesis to apply at least at leading order, and we think or hope that our closed form solution should be pretty valid. So what we do is we use these, we count up the number of scrambles in each numerical scattering experiment and use this as a heuristic proxy for how chaotic the experiment was. What's shown here are maps of the outcome space for numerical scattering experiments. So in each of these maps, the x-axis is the final eccentricity of the binary that survives disintegration, and the y-axis is the cosine of its orientation with respect to our reference direction. In the top panel, we're looking at the full ensemble of order 10 to the 5 scattering experiments we did. And in each of these experiments, we have equal mass particles and the same energy and angular momentum. What we see is that while there is a chaotic sea, the colors which correspond to triple lifetimes vary quite a bit, there are also these clear geometric features floating on top of it, which represent projections of volumes of regularity onto this two-dimensional surface. But if we decide to exclude all of the simulations which don't have at least one scramble, these clouds of regularity mostly clear up. And if we exclude everything that has less than 2 scrambles, they're totally gone. So we see that this heuristic criterion seems to work fairly well in removing the regular parts of phase space. Okay, so with that in mind, here's a quantitative comparison. On the x-axis, we have the energy of the final binary normalized to the total energy of the system, E0. On the y-axis, we have the differential probability of finding a metastable triple at some, of finding the binary left over from triple disintegration in some little cell of energy space, EB. The different colored curves correspond to the different closed form predictions of our ergodic formalism. The colors correspond to the total angular momentum in the scattering. So green is a very low angular momentum scattering, purple is a very high angular momentum scattering, blue is somewhere in the middle, and the data points with their Poissonian error bars correspond to the results of our numerical scattering experiments. And you can see, I mean, qualitatively it's going in the right direction, but the agreement isn't that close. However, if we look at the smaller sample, where we have at least one scattering, or the slightly smaller sample, about 50% of our experiments, where we have 2 or more scatterings, we see perfect agreement within the error bars for the blue and purple samples. So these are the high angular momentum scattering experiments and theoretical predictions, and pretty good agreement for the green one. Now, I would say the agreement is consistent within the error bars for the green low angular momentum ensemble over the first 2 orders of magnitude in probability, but there is clearly a bit of a high energy tail that our analytic predictions are missing. So this may represent sort of a 1% breakdown of the ergodic hypothesis we've invoked. It may represent some sort of rare numerical error in these low angular momentum simulations. This is still something we're looking into. It may also represent, I'm sorry, I missed probably the most likely explanation, the crudeness of our parametrization of the strong interaction region, saying that the ejections are happening within a dimensionless multiple alpha of the time average size of the surviving binary. Qualitatively, this is correct, but quantitatively, it's missing a few details. We can do a similar experiment for different outcome variables. So here, instead of plotting angular momentum LB as an outcome variable, I've plotted a proxy for it, the eccentricity of the surviving binary EB. So again, eccentricity of the surviving binary is on the x-axis, probability is on the y-axis. Once again, we have analytic predictions that sort of, but don't perfectly match the simulations. However, once you look at the chaotic subset of simulations, again, the agreement is perfect in the high angular momentum case and pretty good in the low angular momentum case. Once again, there are slight discrepancies in the low angular momentum case, and we're thinking about where these are coming from, but I would say the agreement seems fine even for that at leading order. You can do the same comparison for the third non-trivial outcome variable, the orientation of the surviving binary, CB, the cosine of its inclination. Here I've skipped right to the punchline. This is the comparison to the chaotic subsample. And again, we see great agreement for the purple and blue curves, pretty good agreement for the green curve. Here we have a slight excess in green of very retrograde outcomes with CB equal to -1. How much time do I have left? We want to stop at 11:35, is that right? Okay. Sure, if that's fine with you. Okay, so just to qualitatively summarize the quantitative conclusions of our ergodic formalism, what we see is that in energy space, the marginal distributions of energy follow a pretty steep power law. High energy outcomes are disfavored, but not totally suppressed until you get to a very high energy cutoff. So binaries that are like 50 times more bound than the initial binary, which arises due to angular momentum conservation. The steepness of these power laws is usually e to the -4. For very low angular momentum cases, it becomes a tiny bit shallower. In eccentricity space, we see something very interesting. So if you ask an astrophysical dynamicist, what is sort of the preferred distribution of binary eccentricities after a period of chaotic evolution, they would probably say it's a thermal distribution. Why this is called a thermal distribution is a little complicated. It's not worth going into, but there are simple dynamical arguments that it could be a universal distribution of binary eccentricities following chaotic evolution. Mathematically, it's a linear distribution eccentricity. So dn d eccentricity goes as eccentricity. What we find is that this is never the case. So coming back here, this thermal distribution is the dashed black line. It's never achieved either in our analytic theory or in the numerical scattering experiments. Instead, what we see is superthermal distributions. So for high angular momentum ensembles, purple and blue, we see a sort of weakly superthermal distribution. And by superthermal, what I mean is that there's an excess of high eccentricity outcomes. But if we look at low angular momentum ensembles, the green curve, it becomes much more superthermal, and there's an even bigger excess of high eccentricity outcomes. The weak superthermality seen for these high angular momentum ensembles can be understood geometrically. It's not that interesting, but the strong superthermality in green can be understood as a consequence of angular momentum starvation. When you have very little angular momentum in your metastable triple, as is the case for the green data points, in order to get a circular orbit surviving binary, you really need to fine tune the trajectory of the escaping star, because a circular orbit is a lot of angular momentum. You have very little angular momentum in your budget. So you need the escaping star to go off in just the right way with a very high velocity and a very large pericenter. It can happen, but geometrically, in the geometry of phase space, it's disfavored. This is very interesting astrophysically, because these high eccentricity outcomes are how you make gravitational wave sources in dense star clusters. So the gravitational wave in spiral time is a very steep function of binary eccentricity. And usually when you have a chaotic scattering in a dense star cluster and you're left over with a black hole binary, it's not an interesting binary, because its gravitational wave in spiral time, the time it would take to merge and emit gravitational waves, is much longer than the age of the universe. The only reason that this is an interesting theory is that for the subset of very high eccentricity outcomes, that gravitational wave in spiral time becomes shorter than the age of the universe, and therefore an appealing source of the gravitational waves that we see. So learning that the generic outcome of these chaotic three-body scatterings is superthermal with an excess of high eccentricity outcomes is very astrophysically exciting. I should mention that since our paper came out, we submitted it to Nature, and it was published in 2019. There have been a couple of interesting follow-up developments from groups here in Israel. So to start, there's a group of astrophysicists at the Technion, led by Chagai Peretz with his student Barry Ginat, who've extended our ergodic formalism to also make statistical predictions for the intermediate states in non-hierarchical triple evolution. By intermediate state, I mean these periods of time between scrambles when you have long quasi-regular evolution. One of the stars has been kicked out to a distant turnaround point, but not an infinite one. It's going to come back eventually. And while that third or tertiary star is flying away, the system is basically decoupled and is evolving in an almost regular way. What is the distribution of binary properties in these intermediate states? Barry and Chagai showed that you can make very similar ergodic arguments to write down that distribution, which is also interesting for gravitational wave sources. Now, at my own institution, the Hebrew University of Jerusalem, shortly after I arrived in Israel, I had a lot of interesting conversations with Barak Cole, who's a high energy theorist. He specializes in sort of classical field theories, I think one could say. And Barak came up with a sort of different interpretation and application of the ergodic hypothesis to this three-body problem. And Barak's statistical formalism is quite a bit different from ours and the one adapted at the Technion. I think the jury is still out on which one is more correct or useful. Both are, at the current moment, both are very complementary. What do I mean by this? What I mean by this is that when it comes to predicting discrete outcome variables, Barak's approach, which is a little too complicated to explain here, but you can ask me later if you're interested, is much more accurate than ours. The discrete outcome variables of this problem are essentially branching ratios. If you have three unequal masses, you might want to know what's the probability that mass 1 is the escaping single star? What's the probability that mass 2 gets incorporated into the surviving binary? Our formalism can make predictions about this, but the predictions are only accurate at the factor of 2 level. They're not that great. Barak's formalism makes amazingly accurate predictions that are accurate at the percent level, but the weakness of Barak's version of the ergodic hypothesis is that it can't make predictions about the kind of continuous outcome variables I've been showing you so far, things like binary energy, binary eccentricity, etc. So Barak and I are in fairly regular contact trying to understand how these two different invocations of the ergodic hypothesis can be married or not. But I would say we don't have a final answer yet. And so if I have a little extra time, I guess 11:40 it sounded like we want to shoot for, I'll go into a bit more detail about applications of this to gravitational wave astronomy. So what's shown here are famous images from LIGO's and the human race's first ever gravitational wave detection You may have seen these in the past in talks by OFEC. What's shown in the top panels are essentially time domain images of the gravitational wave signals seen on Earth when two binary black holes merge with each other. On the y-axis in the top panels, we have the gravitational wave strain, which is essentially a measure of the deformation of space-time when a gravitational wave passes through you and me. So the gravitational waves that are passing through us every second of our lives are periodically deforming the space-time we live in. At one moment, they're making you get a little skinnier and a little taller. At the next moment, you're getting a little shorter and a little fatter. What the gravitational wave giveth, the gravitational wave taketh. The y-axis is a dimensionless measure of this deformation, essentially delta x over delta x, and the x-axis is time. And what we can see in the top panels are the raw data. In the middle panels, these ones, the theoretical waveforms predicted by numerical relativity simulations, and this intermediate panel is the residual, and we see pretty good agreement. In the bottom panel, we see an analogous measure of this signal, but in the space of frequency versus time. So LIGO's been running for a while. It's assembled a very impressive catalog of gravitational wave mergers. New mergers are being discovered all the time, which is why figures like this rapidly become out of date. In fact, this one is quite out of date. I apologize for showing the old version of this figure, but it's still pretty interesting. So what's being shown here? This is a catalog of compact objects whose masses we measured in the universe. The x-axis is meaningless. The y-axis is mass in units of the solar mass. So at the bottom, we have low mass compact objects, neutron stars. In yellow, we have the neutron stars whose masses have been measured via electromagnetic radiation. These are mostly from within our own galaxy. In orange, we have GW 170817, the LIGO-Virgo collaboration's first binary neutron star merger. Orange are the initial neutron star masses, and this is the final mass of whatever compact object was formed after the merger. Higher up on this logarithmic mass axis, we have black holes. So in purple, we have the black holes, again, mostly in our own galaxy, whose masses have been measured through electromagnetic emission. They have some plasma circling around them in the form of an accretion disk. By looking at the X-ray spectrum of this plasma, we can back out the mass of the black hole. But further up, generally, in blue, we have the binary black holes whose masses have been measured by looking at their gravitational wave signals. So in blue, we have pairs of black holes which merge and become a more massive black hole. This is very exciting. It gives us lots of ways to test Einstein's theory of general relativity in strongly curved and even dynamical spacetime, which is fantastic because these aren't properties of spacetime that can be accessed in terrestrial laboratories. But as I said more towards the beginning of my talk, there's still this unanswered zeroth order astrophysical question: where are the binary black hole mergers coming from? We have a few constraints to try and winnow down different competing theories. First, we know something about the volumetric merger rate. Given how sensitive the LIGO and Virgo detectors are and how many binary black hole mergers they see, we can do a little statistical analysis and try to back out the volumetric merger rate, which right now is constrained to be of order 20 mergers per cubic gigaparsec per year. As a reminder, a parsec is about 3 light years. So that's a very large volume LIGO is studying and a very low volumetric merger rate. We know that the binary black holes that are seen by LIGO Virgo have relatively large masses. And by relative, I mean relative to the previous sample of black holes we had detected electromagnetically. As you can see in this plot, the black holes seen via their gravitational wave emission are statistically coming from a much more top-heavy distribution than the black holes seen electromagnetically. Part of this may be selection effects. LIGO is certainly more sensitive to gravitational waves from higher mass systems, but different people have argued that it's not just a selection effect, and there really is an underlying distribution, which is different than the underlying distribution of black holes we had seen in the past. When these things merge, so during the final seconds, sometimes milliseconds of their lives, where we see the gravitational wave signals, the orbits are quasi-circular. There's no detectable eccentricity. The upper limit is usually of order 0.1. And measuring the spins of the black holes, which in addition to their mass is the other astrophysically relevant property they have, is hard to do. But what LIGO and Virgo can measure reasonably well is this parameter called chi effective. So chi effective is the projection of the two black hole spins onto the orbital angular momentum vector weighted by mass. It's a number between -1 and 1. Generally speaking, what we see is consistent with 0, although there are exceptions. What a chi effective of 0 means is either that the amplitudes of the spins are very low, so the black holes that are merging are close to not spinning, or the orientations of the black hole spin vectors are close to orthogonal to the orbital angular momentum vector, so that the projection is close to 0. So these are sort of the limited, the currently limited number of empirical constraints we have on any theory for binary black hole formation. In the future, LIGO will find many more black holes, so these constraints will get better and better. Right now, they're not so tight. So how do these binary black holes form in the first place? One way, which might seem pretty logical, is through binary massive star evolution. We know that black holes come from the evolution and eventual death of massive stars. We also know empirically that massive stars don't tend to live alone. They overwhelmingly live in binaries or hierarchical triples or even higher order multiples. So it's very natural to think that maybe you have a pair of massive stars, they both die, they turn into black holes, then the black holes merge. It seems appealing, but the devil is in the details. The problem is that when these massive stars evolve, they expand to become giant stars. The radii of these giant stars is enormous, comparable to an astronomical unit, the distance that the Earth orbits the sun with. If you have stars whose initial separation is less than an astronomical unit, they won't evolve to independently become two different black holes. The first one to evolve off the main sequence and become a giant star will swallow the second one, and their cores will merge before black holes are formed. So you only get one black hole out of the pair. On the other hand, they could be on a very wide orbit, in which case they can evolve independently to become a wide binary black hole system. But the problem then is that the orbit is too wide to merge within the age of the universe. The leftover binary black hole system is too big to produce gravitational waves, except in the far future. Now, one way to get around this is to say that something kind of funny happens when one star engulfs the other star. Maybe the engulfment can be terminated before the two cores merge, and you could be left with two isolated cores at small radii, which eventually turn into black holes, and then later on merge. But this is a very messy hydrodynamic problem. It's essentially impossible to simulate self-consistently from first principles with modern computers. People have idealized models, but they're not very good. Forgive my French. And so it's very unclear whether isolated binary evolution works. So an alternative possibility is the one I described at the beginning of this talk: dynamical assembly through iterated chaotic three-body scatterings. There are more exotic channels that have been proposed as well, and which have been studied. Actually, I would say some of the leaders of the study of these are astrophysicists here in Israel. So one possibility involves Kozai-Lidov cycles. This is a secular dynamical effect in hierarchical triples. So if you have a tight binary, if you have a binary of black holes that's orbited at a large distance by a hierarchical tertiary, the time averaged or secular torque from that tertiary can pump up the eccentricity of the inner binary and drive it to merge. Another possibility, which my student Shmuel Gielbaum has been investigating for a couple of years now, is hydrodynamically driven mergers when wide black hole binaries find themselves in a very gas-rich environment, like a so-called active galactic nucleus. I'm a little biased and I like this channel, but that's just me talking. I think we're about out of time, so I'll just leave this question as the open problem it is. I have my own ideas about which of these channels are more likely. I'm in the process of applying my analytic formalism for understanding chaotic three-body scatterings to make better predictions about this channel. But I think it's fair to say that at the present moment in time, all four of these are viable contenders for explaining the bulk of gravitational waves seen by the LIGO-Virgo experiment. None of them is obviously the dominant channel or obviously subdominant. Of course, it's also possible that more than one of these is contributing at an order unity level, which would be very exciting for theorists who like making predictions about dynamics. But I think this is probably a good stopping point. So I'll skip ahead a couple of slides and just leave you with conclusions. The basic takeaway I hope you have from this talk is that even though non-hierarchical triples are very chaotic, and that chaos makes it very hard to come up with a deterministic pen and paper solution, you can use that chaotic nature of their dynamics to write down a pen and paper statistical solution, making use of this concept of ergodicity, the idea that no one part of phase space is favored over another, so long as you're talking about energetically permitted parts of phase space. This ergodic formalism that we've written down gives closed form predictions for the outcomes of non-hierarchical triple evolution. They generally agree pretty well with direct integration of the equations of motion in big ensembles of numerical scattering experiments. There are a few loose ends. There are interesting deviations at sort of next to leading order, especially in low angular momentum ensembles. These are things we're thinking about, but we don't really know what the answer is yet. So I guess a little more generally, one thing I will say is that this is one of the only examples I know of this kind of ergodic disintegration argument being applied to a classical system. These ergodic disintegration arguments have a longer history in quantum mechanics. They've been applied for a long time to think about how complicated multi-body systems like radioactive nuclei could decay, how mesons could decay, for example. Fermi first wrote down a theory like this to think about meson disintegration in the 1950s, but there are very few examples I know of this being applied to a classical system. So more generally, I guess one sort of high-level takeaway I have from this is that it's very interesting to try and come up with classical systems with well-defined end states where you can make this sort of statistical argument. And I suspect there are many more lurking out there, especially in astrophysical dynamics. But here, at least, this was a fruitful one to apply this kind of ergodic disintegration argument to. So I'll wrap up here, and if you guys have any questions, I'm happy to take them.
Thank you very much, Nick, for an excellent talk. Okay.
So we believe that you assume that all these stars in the particles are mass point particles.
Uh-huh.
So where is the physical situation where we have the finite size of the stars? So it can be probability that two stars will collide.
Yeah, that's an excellent question. So our assumption that the particles are Newtonian point, that the stars are really Newtonian point particles will break down if they have very close passages by each other when short-range forces can enter the picture. Things like tidal forces, relativistic corrections to Newtonian gravity, even direct physical collisions, like you're saying. You can actually calculate in a statistical way the probability that one of these systems will have such a close encounter that Newtonian gravity is no longer a great approximation. The probability depends on the distribution of initial conditions you care about. So again, I have to give you a slightly unsatisfying answer. In general, if you're looking at an ensemble with very large energy, by which I mean very negative total energy, E0, then the system is very tightly bound and close passages are more common. So our assumption will not be as good. On the other hand, if you're thinking about an ensemble that's more loosely bound with an E0 that is closer to 0 in magnitude, this will be a better assumption. For the kinds of non-hierarchical triples that form in globular star clusters, it's quite rare to have such a close encounter that the Newtonian point particle approximation is bad. In denser and more energetic star systems like nuclear star clusters, these kinds of encounters you're talking about will be more frequent, and this assumption will not be as strong. But at least for globular and also open clusters, the distribution of energies, E0 you get, makes this assumption pretty well motivated. Yeah, thanks for the question. Mm-hmm.
Despite that they have zero measure. Also in regular first theory, periodic orbits have a zero measure, but still they can give advantages of the first exponent of the first. Yeah, so here, can I use what are the fingerprints of families of exactly sort of physics in our approach? Are there some fingerprints?
That's a super interesting question. Should I repeat it for people joining remotely? Oh, okay, so the question was in many chaotic systems, including the three-body problem, you have measure zero families of perfectly periodic orbits, ones which close on themselves in time as they repeat over and over again. And indeed, there are many such orbits for the chaotic for the non-hierarchical three-body problem. They are, as you said, a set of measure zero. So from an astrophysical perspective, we're not going to find black holes in the universe on one of these perfectly periodic orbits. But as you say, these are often useful for understanding the structure of phase space, sort of the divisions sometimes between parts of the chaotic sea and islands of regularity. Unfortunately, I don't think I can tell you how the periodic orbits in the non-hierarchical three-body problem structure this phase space, because to my knowledge, they're not fully known and classified yet. People have discovered individual periodic orbits in the non-hierarchical three-body problem, but my understanding of the literature is that they're not fully, they've not been fully discovered or categorized yet. So right now, I can't give a very concrete answer about how they structure phase space or help to determine Lyapunov exponents. It's an interesting question, but I think right now we're limited by the lack of knowledge about where these periodic orbits actually live and what their properties are.
First, I guess that you have a good operational definition of scramble, but it's one scramble, two scramble, and so on, because you may have little that you have to interpret somehow. But given that you have such a definition, can't you start from a single initial condition or just slightly perturbed single initial condition and show how, as a function of the number of scrambles, the distribution of outcomes is getting closer and closer with the number of scrambles to the expected exotic distribution?
Yeah, that's a great question. To some extent, we can see it happening in this series of figures. So as a reminder, this is the marginal energy distribution, the density of states, if you want to be a little pedantic. And the points show scattering ensembles where we haven't cut anything out. And so here we see the agreement is not that great. If we cut out about a third of the sample, so removing everything with zero scrambles, we see that we're getting better agreement. The number of scrambles is shown in the top right. The agreement is better, but it's still not perfect. And in particular, there is a deviation in all the ensembles at this point right here that largely goes away if we are a little more restrictive and say we'll only bin up the outcomes with 2 or more scrambles. So we can see this convergence. It seems to happen pretty quickly. We go from this situation where none of the scattering experiments are consistent within the error bars. After the first scramble, the low angular momentum ensembles are almost consistent. There's just that one deviation up. You have an excess of events with like triple the total energy. And then after two scrambles, the agreement becomes very good, except for this high energy tail in the low angular momentum case. So you can, and I should say, this tail does not go away if you keep doing this. So if you become more restrictive and say, we want 3 scrambles or 4 scrambles, this tail does not go away. So our guess is that either this represents some sort of breakdown of our admittedly crude ergodic assumption. So maybe there are resonances or a finer structure of the islands of stability in the low angular momentum case that produce this. It may also represent a failure of our admittedly crude limits of integration, this parametrization I talked about earlier. We're trying to figure out which one of those it is, or potentially it could be a numerical error, although we think that's unlikely.
I think we'll be the last question.
There's no time? So it was hard to follow. This was a power law distribution, and that potentially can be very badly behaved. I don't know what the powers were because it was flashed quickly, but like this typical behavior is it very different than average behavior? Do you see any effects of rare events?
Yeah, that's a good question. So the energy power laws are not fat-tailed. So the question for those at home was, power laws can be ill-behaved. I think you're getting at, is this, are these fat-tailed distributions? The short answer is no. So the power laws are relatively steep, somewhere between e to the -4 and e to the -3 halves, depending on the angular momentum of the hypothetical ensemble. They also do have cutoffs at very high energies. So these are super exponential cutoffs, and the probability goes to 0 at the highest energies. So ultimately, these are not systems where the mean value or the variance is dominated by the highest energy outcomes. Good question.
Nick is going to be here. He has to leave around 2 each. Is that right?
I apologize. I have to teach my grad seminar at 4 p.m. today.
If you have more questions, then you can come to it afterwards. So thank you very much for an excellent talk.
Thanks again for having me.
See you all next week.